I'm Dr. Monica Bennett, and I teach physics and biology for the Well-Trained Mind Academy. I've taught for the Academy for 7 years. Before that, I earned a Bachelor of Science in Physics at the University of Dallas. One of my favorite things in my educational background was getting to have the best of both worlds in earning a physics degree at a liberal arts university. And after that, I earned my PhD in physics at Vanderbilt University. My research for the PhD focused on the physics of fruit fly development, and so that introduced me to something that continues to inspire me now as a teacher, which is that many of these fields of science that are taught, especially in introductory classes, as being separate fields, turn out to be interconnected in all kinds of wild and wonderful and unexpected ways once you dig deeper in and once you start being able to ask the kinds of questions that researchers are currently asking. So biophysics is just one of those areas where what seem at first to be two separate fields of science really intersect in fascinating ways. So now, as a teacher of both physics and biology, I really try to bring that inspiration that I always get from the fact that there's so much to be learned from new science that is happening every day. And to understate it mildly, there is a lot of science out there. So one of the things that I love about teaching science, as with any teaching job, is that part of my work is to be constantly learning and figuring out how to pass it on and share it with others. So I get really excited about figuring out a balance every year between the science that is in the textbook that forms a great background and a foundation for understanding the basis of any field of science, and then being able to see how those basic ideas and that basic knowledge continue to be used by researchers in cutting-edge topics and new discoveries. So in my classroom, I really love to bring those together and to show not only what the basics of physics or biology are, but also how those continue to be used and to be useful as we learn more about our universe every day. What to expect in the classroom. I teach both the logic and the rhetoric stage. In the logic stage, the class is divided into topics or units, and for each unit, students can expect to write a summary of a reading. So we'll practice the skills of writing a narrative summary as it's practiced in Well-Trained Mind writing courses, and also to carry out a science experiment at home, an experiment that is themed around the topics of that unit, and then to work up to writing a full lab report about the findings. Those are the basic assignments that will be the rhythm of the class for most of the year, with occasional other things like one written project and a science fair project. For the rhetoric stage, we also organize the class by units. There is a little bit more that goes on there. There's a regular rhythm of discussion boards, which give the students a chance to engage with topics beyond the basics that we will have time for in class and from the textbook, and then a regular rotation of quizzes and tests that give students a chance to show what they've learned, and in the case of the quizzes, to practice a little bit and ramp up to what we might consider the summative assessment that happens in the test at the end of each unit. Those are the basic rhythms of class, and then other special types of assignments do come up throughout the year and allow students to show other skills working on their writing and their communication in different ways. Before class with my rhetoric classes, because we are trying to learn science in 2 hours of class time a week, students can expect to do some reading or viewing before class begins. And it's a bit of an entry ticket rather than an exit ticket, so that students can come in having seen the material we'll cover and hopefully having questions ready to ask and to discuss. That's what the classroom looks like in terms of assignments day in, day out. As far as classroom engagement, you can expect a combination of lecture with continual feedback from students. I like to take questions from the students and use those to shape the order and the extent to which we cover different topics in class. I make time for extra questions about topics of interest whenever I can. Along with those lectures, I engage students regularly with polls and other methods of answering questions and discussing during class time. We have group work. We spend a lot of time exploring some of the wonderful simulations and animations and videos that are out there and available to help explain beyond my drawing skills and my verbal explanations. So you can expect a lot of different types of engagement in class and a lot of extra resources and enrichment that I provide on the side, so that anybody who wants to spend time either digging deeper into the basic topics from class or going beyond them to some of the other interesting things that build on those topics. There will always be something for you to take away from class and continue with if you want. And of course, beyond and outside of class is where students will carry out most of the actual assignments that are on our class calendar. Most of those assignments will need to be done outside of class time. And I also always encourage students to look at other resources like the section review questions at the end of our textbooks. But those are things that are rarely, if ever, assigned as homework. I do try to respect the time and limit the workload of students beyond what we do together in class. That brings us to, what do I want students to get out of my class? In addition to doing all the assignments and learning all the facts, what I really want most, first of all, is for students to feel that they understand a little bit more about what science is, not just a definition in the dictionary, but what it means to think like a scientist, what people are doing when they do science, what it means and what it doesn't. There is so much that is being discovered and that has yet to be discovered. So what I love is when students leave my class feeling comfortable asking questions, considering and trying to answer questions, and feeling confident in their own ability to understand new concepts and to identify their own areas of interest and their ability to research and dig further into those areas and find good sources to learn more for themselves. One of my favorite things is when I can see students getting engaged with a topic that they didn't even realize existed. And this is where, again, I love to introduce new areas of science, things that are on the cutting edge, things that might combine topics that you would never have thought of, but somebody is out there researching. So to that end, some of my very favorite assignments are the ones that allow students to choose and really focus on a passion like that, that connects to our subject and our topics. So our research papers in the rhetoric stage classes, the science fair project in the logic stage physics class, and in my lab courses, the chances that students have not only to do the experiments that I set out for them, but also to choose their own lab topics from time to time and to design an experiment that really helps them to pursue something that they are passionate about. Wherever I can, I give that kind of flexibility in my classes so that students can find what they're interested in and put that together with the basic ideas that they need to learn to be able to appreciate that, understand that. So, having heard a bit about what I try to do in class, you can check out my teaching sample up next to see how that looks. Hello, this is Dr. Monica Bennett with a brief teaching sample about musical notes and harmonics. In this brief lesson, we'll talk a little bit about the nature of sound waves, specifically mostly as that relates to how we experience them with music. So that means talking a little bit about the idea of frequency, and then ultimately talking about the idea of harmonics and how important that is to what we think of as the musical experience. So first, a little bit about sound waves. Waves generally come in two flavors as far as the general shape of the wave. So there is what you might think of, first of all, when you think of a typical sine or a cosine wave. And if you will excuse my imprecise drawing here, that might look something like this. So there are some clear things that you can measure with a wave like that. You can look at the crests and troughs, the ups and downs. You might be able to imagine measuring the distance between those parts of a wave pattern to find what we would call the wavelength. You might be able to imagine measuring the height of the wave from a midline. And those are all things that are pretty easy to identify and to imagine with this type of wave, the up and down, the sine or cosine wave. Sound is not like that. Sound is what we call a longitudinal wave, and it means that instead of an up and down, there's more of a back and forth pattern. I will show you what I mean, actually. So one of the things that I like to use in class a lot is various simulations and animations to show this kind of thing. And for a longitudinal wave like sound, the best way to look at it really is to look at something in motion. So this, by the way, is an example of the kind of wave I was just describing. So if we look at a water wave being formed from the side, it might look something like this. And so you can see the ups and downs, the crests and the troughs. A sound wave, as I said, does not look like this. It looks more like this. So I'm going to set this to show the particles. There is no wave here at the moment. You're just seeing air particles, probably air, kind of just meandering around, bouncing off each other a little bit. With a wave, you can notice that starting from the speaker on the left, you now have these areas, and they're starting to spread out. I put this in slow motion so that you can not only see the way that the wave spreads, but you can also see the way that the individual particles move. So one of the important things about a sound wave is that if you're watching individual particles, and especially you might watch one of these red ones, that red particle, whichever one you're watching, is not actually being swept from left to right as the sound wave goes through that area. It's bouncing back and forth, and so it's actually parts of different parts of the sound wave. It participates in the same pattern over and over again in different places. Sometimes it's part of a high pressure area, sometimes it's part of a low pressure area. And that's the way that a longitudinal wave like sound travels. So that's important when you consider some of the more in-depth things of what happens with a musical instrument, which we're not going to get into today, but especially the way that air travels in pipes and the way that air pressure is affected. So this is what we look at basically. And so sound can travel through any medium or any substance that's capable of having its particles move like this. And sometimes having the particles be more packed closely together and more tightly bound, like in a metal, for example, can even make sound travel faster. For example, sound travels about 15 times faster through steel than it does through air. So, fun facts. As we look at this, I can also introduce a very important idea, which is the frequency. So I'm actually going to turn this to normal speed now, so you can see what you were missing before. This is the normal speed of this sound wave propagation or travel. And I had turned it down to slow so you could track those red particles a little more easily. So this is what we would call a high frequency sound wave. And if you look at this, you get an idea of about how many waves are traveling through this space. You can also get an idea that gives you a measurement of what actual frequency means, which is how many waves are being produced per second. So the higher the frequency, the more waves you have happening per second. And if I crank this way down toward the minimum, give it a second for that change to spread throughout the simulated space, and you'll see that these waves are now, the waves are not actually moving slower, but there are fewer of them being produced every second. And that's what frequency means. It's telling you how many waves are being produced per second, typically per second, and that unit, waves per second, is hertz, which you may be familiar with. It's capital H, lowercase z, and it's very common to see that used for sound waves to talk about that frequency. So now you've seen this is low frequency. There are just fewer of those waves every second. But if you took a look at the timing, if you used one of the tools here, like a stopwatch, you would be able to see that the sound waves aren't necessarily traveling more slowly. In fact, if it's the same type of air, they shouldn't be traveling more slowly. The difference is just how many new waves are being produced every second. So that's what the frequency measures, waves per second. And again, very important concept for talking about differences in sound. So let's go back then to our slides here, and you can see that there is a link here. I will do my best to make sure that these slides are available along with the video of this teaching sample, in which case you will be able to go directly to this link. But even so, if you want to look into it, you can search for this title by PhET Interactive Simulations. They have fantastic physics simulations. So as we look at that sound, this wave that produces the back and forth motions of the particles, basically anything that can cause vibrations of that kind can cause a sound. So in music, you can think of some of the things that you know of that can cause that kind of thing. The vibration from the plucking of a string, from the hitting of a membrane, like in a percussion instrument of some kind, from the vibration of a reed or a brass mouthpiece, from the vibrations of your own vocal cords. These are all ways that sound can be produced in musical instruments. And then as long as there is air or something else surrounding that instrument, the sound can be carried outward. So unfortunately, if you play your violin in a vacuum, that sound will no longer travel to the observer. But as long as there is something like air between the violin and somebody else, they'll be able to hear that. So we've introduced this idea of frequency already. As I said, it's just the number of waves that are happening per second. That doesn't tell you anything about how fast they're traveling. So it does not have to do specifically with the speed of sound, but it tells you how many of those waves are happening. And this actually relates directly to something that we experience as humans, which is the idea of pitch. So you know sort of what pitch means to you. You might have a hard time describing what it actually means for something to sound higher pitched or lower pitched because you just kind of know. Maybe a higher pitch seems sharper to you. It might seem like it's kind of digging right there into your ears if you hear something very high pitch, whereas a lower pitch might be more the kind of thing that you start to feel kind of throughout the whole body. And that experience of pitch is tied directly to the actual frequency of the sound. So higher frequencies, sounds that have more waves per second, do correspond to what you perceive as higher pitch, and lower frequency, fewer waves per second, is what you experience as low pitch. So that's an interesting thing to keep in mind, that pitch is your subjective experience in your body of this actual idea of frequency, which has a physical objective number attached to it. And your brain and your ear are not generally able to put together that exact information. Here's exactly how many vibrations there are per second. That's not the kind of information that you tend to be aware of from your brain. But you do get this awareness of high and low pitch. And the more you have a trained ear, or to some extent the natural idea of good or even perfect pitch, the better you are at telling those apart and being able to relate pitches to each other. So, as we talk about sound frequencies, another thing to be aware of that's very important for understanding music is that most of the time you're not just hearing one sound frequency at once. Usually, what surrounds you are multiple sources of sound operating and producing multiple frequencies. And so your ear and your brain work together in this wonderfully complicated process that you're not even consciously aware of to help you be aware of and able to interpret what those different sound frequencies are from, where the different sources are, how they relate to each other. And that's how you make sense of this onslaught of different sound waves that's coming at you from different directions at all times. So let's take this to music. We could talk for a long time about what music is without coming into a really good definition, because it's mostly a subjective kind of thing. With physics, we can say a few things about music. One of the things most people agree on is that music usually needs to have some sort of rhythmic arrangement. But whether that is pleasant to people, whether one particular thing is considered music versus another, that's a very subjective question. So today we're going to focus on one aspect of what you can think of with music, which is the idea of sound frequencies. So sound frequencies have a very obvious application if you think about the idea of harmony, where you have multiple notes that are produced together. Maybe you have multiple musicians who are each producing their own note, or maybe you have one musician producing multiple notes, like plucking multiple strings at once, for example. But that is only one way to think about the cause of multiple sound frequencies. As it turns out, even when you play a single musical note, there's a little more going on there than meets the eye. So if you personally play an instrument or sing, and if you have ever tried to be in tune with anybody or anything else, you might have noticed that you usually do that by trying to play the same note as somebody else. Now, if you're tuning up your own instrument, like a stringed instrument, obviously that's a different process, and you'll use the pitches of different strings and different harmonics, which is its own topic. But even when you are playing the same note as somebody else with a different instrument, you might notice that they don't sound precisely the same. And that's because of what we can call harmonics. And harmonics basically tell us that even if you are playing or singing the same note as somebody else, what is the same there is what we call the fundamental frequency. So let's say that your fundamental frequency that you're trying to match with somebody else is a note with a frequency of 100 hertz. So if you play the same frequency there, great. You'll sound like you're playing the same note, but it still won't sound precisely the same between, say, a violin and an oboe and a piccolo or something. And the reason is that on top of that fundamental frequency, you also have these other frequencies that are present in the very same instrument. And we don't quite have time to go into extended physics discussion of why that is. I can show you a source or two that will help you read more about that, including this one, which we're about to look at. But the idea here is that in addition to that base frequency, you already also have these other frequencies that are present in the same note. And these are called harmonics. So even if you just think you're playing a single note on your instrument, it sounds more complex than that. And that's because it's more than just that frequency of 100 hertz. There's also what we call these integer multiples. So an integer is a whole number. And so if you play a base frequency of 100 hertz, for example, then your integer multiples would be things like 200 hertz and 300 hertz and 400 hertz and so on and so on. All of those would be what we call harmonics of your basic fundamental frequency. And there are all kinds of fun math games you can play with these. One of the ones that people recognize the most is if you are familiar with the idea of the octave, and you may have heard of this. That's when you play one C and then you play another C, and your brain interprets that as, oh, those are essentially the same note. But they're not really the same frequency. What they are is they are separated by basically a factor of 2. So when you double a frequency, you get something that is an octave above it. So 100 times 2 equals 200. 200 hertz sounds like a note that is an octave above 100 hertz. And if you take that 200 and you double it again, you get 400. And so 400 hertz sounds in turn as if it is an octave above 200, which is an octave above 100. So that's how you can get up to multiple octaves. And this is where I take you to another link. So this is the link right here. So you can find this for yourself if you want to study anything that we're seeing in more detail. One of the things that it shows is the idea of what these harmonics look like. So if you're plucking a string, very long story short, what you would have is the string vibrating in a few different ways at once. One of them would be this very simple shape that you see here on the left, where it just looks like, it's fixed at the ends and it's vibrating back and forth in the middle, as you might expect if you pluck it right in the middle. But you also have these other modes where it's vibrating in these more and more complex patterns. And these are what those harmonics look like. We don't have time today to get into those. So I'm just going to instead ever so briefly take you up here. And up here, I really like that it gave you what's called the harmonic series. So all these different harmonics where you have these multiples of the frequency, and they're written as notes on a staff. So if you know how to read a bass as well as you might recognize right away, there are a few notes here that you might recognize. There's a middle C, and that's number 4 here. So that is actually not the starting note here, but that's actually the 4th harmonic of that starting note. It is 4 times the frequency of the starting note. And if you go down to that starting note, again, if you can read a bass clef, you might need a moment to recognize it, but it is also a C. So you look at that, the bass note is a C, and then you look at harmonic 2. That's the one that should be double your original frequency, also a C. So that's the rule we learned, that doubles make an octave. If you double that 2, you get to 4, also a C. If you double the 4, you get to 8. Look over here, also a C. If you double the 8, you get to 16, also a C. And you could go on and on like that. So the fun thing about that harmonic series now is that you can see where the octaves are, 1, 2, 4, 8, 16. You can also see there are a bunch of other harmonics there that are not those specific numbers. So you have 3, you have 5 through 7, you have 9 through 15, and there are all these stretches, and the higher in the harmonic series you go, the more harmonics there are that are not actually octaves. And that's where you get into all kinds of other fun intervals. So if you know about music theory, you know about thirds and fourths and fifths and so on, those are the intervals that are there. And so if you read here and a little bit in one of the other links that I have on the very last page of my slides, you can find out more about the way that the classic tuning systems like Pythagorean tuning make use of those exact numbers. So you can look at it and you can say, what is the relationship between two numbers, between two notes rather, if the frequency ratio is a 5 to 4, for example. That's a specific ratio. And you might notice here that that's a third. So you can look at that and you can see, well, what's the ratio between any of these two? And Pythagoras was able to make those calculations and tell you exactly what the frequency relationships ought to be for these very pleasing to his ear kind of musical harmonies. So having said this, there are a few things to do as we round out the teaching sample here. One of them is that I really like, in addition to sharing these links for visuals and simulators, I like to give polls. So sometimes there will be math involved, sometimes there will not. And usually I'll give some time to think about it. In this case, because you can pause a recording, I'll give you a few seconds to do that. And the question here is, if you are playing or listening to a note where the fundamental, that bass lowest frequency, is 110 hertz. Which of the options here do you think would not be a harmonic? So think about what we've just learned, that harmonics are these integer whole number multiples of that fundamental frequency. Which of these would not fit that bill? And I'll give you a few seconds to pause if you need to. Okay, answer time. The answer here would be 55 hertz is the one that is out, because everything else starting from 110, as you multiply, 110 times 2, 110 times 3, you get 220, 330, 440, and 440 might sound familiar, by the way, if you know that as the frequency of a concert A for much of the world. So those are all harmonics of 110. 55 is actually a lower frequency. And so that can't be a harmonic, but it is still in the same line of that math. So you might notice that if 55 were the bass frequency instead, 110 would be a harmonic of 55, but it doesn't work the other way around. Harmonics are only higher frequency. All right, so one more poll for you. And this is looking not just at the harmonics, but thinking about what we said about what it takes to be an octave. So we know that the harmonics are 220, 330, 440, 550, et cetera, just keep multiplying 110 by different numbers as long as you want. But of those numbers, which of these four here is not an octave? So which will not sound as though it's 1 or 2 or 3 octaves above 110 hertz? Again, take a second to think about it. Usually I would give more time. You can pause if you need to. All right, so as you do that math, again, remember that octaves are doubling. So you double 110 and you get 220. You double 220 and you get 440. Double 440, you get 880. And the odd one out here is 660. Now, notice this is still a harmonic. So it is the sixth harmonic. 110 times 6 equals 660. But it's not an octave. And so that would be one of those other intervals, a third or a fifth or a sixth. And you'd have to look at it and look at the different ratios to see exactly how that would come in. All right, so we are a little over time, so this is where I need to wrap up. So things that I hope you take away from this, when we think about sound frequency, that is very tied to what you perceive as pitch. So that impression of high or low pitch is telling you something about the sound frequencies. Most of the time when you listen to sounds, especially musical notes, they're not just a single frequency, which is when you listen to something like an app for tuning or something, and you hear this very sort of pure, maybe sterile kind of sounding single frequency. Instead of that, they are vibrations of multiple frequencies. And when those frequencies are all produced by the same object, and they're all multiples of that lowest frequency, they're called harmonics. So when you pluck a string or anything of that nature, you have a base frequency that determines the overall sound of the note as far as which pitch you perceive. And then you have these harmonics that get layered onto it, and you can't necessarily hear them very well, but they add to the richness and the individual sound of that instrument. So this is what really makes the difference when you listen to different musical instruments, and they each have their own sound, or timbre is the word that gets used for that sometimes. It's because even when you have the same base frequency, those harmonics are present to different extents, and which ones are present and how prevalent and noticeable they are gets modified by things like the shape of the instrument and the materials it's made of. So all of that you could look into at great length, and if you want to do that, I have some links here that I highly recommend. Really, if you want to just get into all of the nerdy physics and music stuff, this is the very best recommendation that I have for you. The University of New South Wales has a phenomenal website on all kinds of music acoustics, but any of these are great resources. So I hope you learned something interesting today and you have something to think about the next time you listen to music, and I hope to see you in class.